small short lecture to, barely a lecture, to wrap up the chapter on vectors. So we will have a test on this in 2 weeks from the 9th, I think. Yeah, whenever that falls, 23rd, it'll check your announcements. I think what I'm going to do is I'm going to write you a test and I'm going to student number personalize it. So what that means is each of you will have a different test. There's only about 15 of you. It isn't too onerous for me to do that. And again, I'll write this in the announcement. It's open book. So I'm going to make it a little bit harder. So the way I'm probably going to do is I'm going to kind of have maybe 40% straightforward stuff, and then up another 30% stuff that's a bit harder, and then the top 30% we push it a little bit. Now I have to stay within the confines of what I covered, but I'll be looking at kind of small little bits that are slightly beyond what's in the manual. Slightly beyond. I mean, I really actually don't have that much scope, so we'll see. I probably can't make it that hard, but it'll be certainly designed that you get 70% kind of handily, and 70% really is the first. And remember that I understand that you just need to pass, so 40% is fine. When you're doing it, as I said, it's open book, so really if you have the manual, you're better nick, and these few pages 48 on are good. Okay, so we see, say, a vector in the plane. You can describe it in terms of x and y coordinates, or in terms of magnitude and direction, and the direction is in the angle with the positive x-axis. You can do the same in space, but we won't bother talking about the angles. Certain distance along the x, certain distance along the y, certain distance along the z. And you find the magnitude with Pythagoras. The adding vectors, this is basically down the bottom left, is just saying adding vectors is easy. It just works exactly the way you think it would. This is just kind of demonstrating how you add vectors together in terms of a picture. Scalar multiplication. So I think what's missing here is the origin. So if you got a vector A and you multiply it by a positive scalar, that's bigger than 1, you get a longer vector in the same direction. If you multiply by a negative scalar, for example here, -1, you get the length will, like if you multiply by -1, so I'm saying here the length of minus A is the same as the length of A, but it's in the opposite direction. Okay, this is just saying, how do you do scalar multiplication? You multiply everything, all the components, by the scalar. What I got here, unit vectors, I, j, k. I means 1 along the x, that's what this is saying. J is 1 along the y, and k is 1 along the z. And this is a unit vector. You take a vector and divide it by its own length. You get a vector of length 1 in the same direction. This is the displacement. Now this can be from a vector to a vector, or alternatively from a point to a point. Say if that is P and that is Q. Now I don't really need those vectors there. Here's the origin. The vector that goes from P to Q, vector from P to Q in this sense is the point coordinates point B, Q, excuse me, minus the coordinates of point P. So that's basically another way of saying that. We have our scalar product, which is very easy to calculate. You just multiplies the x, look, the x with the x, plus the y with the y, plus the z with the z, and add them together. The important thing is it's a number, and we got a relationship between what we've been calling the algebraic, the coordinates, and the geometry, which is the lengths of the vectors and the angle in between, and that allows you to find the angle in between two vectors. And we have that vectors are perpendicular exactly when their dot product is 0. This is the right hand rule. So if you open up your hands like this, with your thumb going up, and sweep your fingers from B to A, the position of your thumb, in this case up, is the first vector times the second. So this will be the direction of B times A. And the magnitude of this vector is AB times the sine of the angle in between. How do you calculate these things? Well, you do this determinant business. And what have we got? We've got the work done by a force is the dot or scalar product of the displacement with the force, and the moment, which is a vector, is the vector product of those.